Friends, today we will study the numerical integration methods for solving a set of ordinary nonlinear differential equations. We have developed the mathematical model of the system for analyzing the stability. We have developed the mathematical model for synchronous generator, excitation systems, turbines and governors, and also loads. Okay. Now, when we want to analyze the tangent stability of the system, we need to solve a set of non-linear ordinary differential equations along with a set of non-linear algebraic equations. And we can say that we have to solve the differential algebraic equations. For solving the algebraic equations, we have standard techniques available like say Gauss-Seidel technique, Newton-Raphson technique and so on. Now, for solving these nonlinear ordinary differential equations, we have to resort to numerical techniques, because there is no analytical solution available for nonlinear differential equations. Now, the numerical techniques will provide you approximate solution. I am emphasizing this word approximate solution. Here, when I say that we apply numerical technique for solving this problem, what we do is that the time duration over which we want to get the solution is divided into small time segments. We can call these time segments starting from initial time t equal to t0 to t1, t2, t3, t4 and say tn. And these segments may be equidistant or of the equal length or may be unequal length. That is, the time step from initial value t0 to t1 and from t1 to t2, these two time steps or so on may be equal or unequal. Now, today we will study these numerical techniques, and broadly these numerical techniques are divided into two categories known as the explicit integration methods for solving a set of ordinary differential equations. We use the word explicit integration methods, and another technique is known as the implicit integration methods. We will be in a position to understand what is the difference between the implicit and explicit integration methods and their merits and demerits, right, as we will discuss the different techniques. We will under the explicit integration methods, we will discuss briefly the Euler method, modified Euler method and fourth order Runge-Kutta method. Although a number of other techniques are available in the literature, right, but however, we will confine our discussion to these three techniques which come under the category of explicit integration methods. We shall discuss one simplest technique under the heading of implicit integration method, that is called trapezoidal rule. There is a trapezoidal rule of integration. Okay. Now, to understand the solution of ordinary nonlinear differential equation, we start with the a general differential equation, general nonlinear differential equation of the form dx by dt equal to f of x t, where x is a vector. X is a vector. It will have its dimension depending upon the size of the problem which we have to solve. For example, in the classical stability analysis, the x will comprise of the angles, the rotor angles deltas and rotor speeds, like say delta 1, delta 2, delta n if it is n machine system, and the speeds like say omega 1, omega 2 up to omega n. These will be the state variables. Then we will come across a set of differential equations which are put in the compact form as dx by dt equal to f of x t. For solving these equations, we know the initial condition, that is time t equal to 0, x is equal to x naught. That is, the initial conditions are known to us, and in knowing the initial condition we have to find out how the x varies as a function of time. That is what is the meaning of solving this differential equation. That is, we want to get the solution for x as function of time. The Euler method is the simplest of all the methods, and let us consider a scalar system. That is, we have only one unknown to be solved. To understand the Euler technique, we will start first with the scalar differential equation, that is dx by dt equal to f of x t, where x is a scalar. Right. Now, to solve this, what we know initially is that x equal to x naught at t equal to t naught. This is the initial condition which is given to us. For example, when you solve our swing equation, right, at time t equal to 0, we know what is the value of delta, that is delta equal to delta naught at t equal to t 0, right. This is initial condition. Now, to understand how we obtain the solution of this, let us assume that the solution for x as a function of time is known to us. I will say that this is the exact solution of this, that is x varies as a function of time by this very nonlinear way. This is the initial point, this point is t equal to 0, and corresponding to this the x is equal to x naught. This is the initial operating condition. Okay. What we do is we find the derivative of this function, that is this function, that is obtain the derivative at x equal to x naught. It means we are basically finding out a slope of this curve at x equal to x naught, and let us say that this line represents the slope at x equal to x naught, right. Now, let us take a small time step and call this time instant as t1, where this time step can be denoted by delta t, that is t1 minus t0 equal to delta t. Okay. Now, if this we take a small value of this step, right, then value of x at t equal to t1 can be represented by this equation. That is, first we will find out what is the change delta x, that is this quantity delta x, that is at t equal to t1, right. We find out the value of x, that is x is equal to x naught plus delta x. The delta x is the change when you increase the time by a small step delta t, right. So, that now we can write the solution in the form that is x1 equal to x naught, the initial value, plus dx by dt at x equal to x naught into delta t, right. This is what is the approach we make use of in the Euler method. That is, you find out the slope of the curve at t equal to t naught, that is x equal to x naught, right, and then find out actually the delta x, that increment in x when t is changed by time step delta t. Now, this increment is determined by this expression, that is dx by dt at x equal to x naught into delta t. Now, here this Euler method can be considered to be the first order method. That is, suppose you expand this function, if you expand this function around initial value x naught using Taylor series expansion, then the Taylor series expansion will give you x1 equal to x naught plus delta t into x naught dot plus delta t square by factorial to x naught double dot and so on. That is, if we take any function and expand at the initial operating condition using Taylor series expansion, then x1, that is the new value at time t equal to t1, can be obtained as by this series. That is, here effectively we are truncating this Taylor series by considering only the first order derivative. Okay, these higher order terms we are neglecting, and therefore obviously the accuracy of solution will depend upon delta t. If I take delta t very small, then naturally the x1 will come out to be very close to the actual value, right. Now, here when we use this Euler's method, we assume that the slope of this curve is same all through the interval, while if you see the actual solution, right, then during this interval the slope is different at different points, right, and therefore there is some error that will be incurred actually when you solve using the Euler's method. For example, if you get this point, that is x equal to x1, I will call it as x1 corresponding to t1. Now, if you want to find out the next step, that is, you want to find x2 using x1, right. Now, what is going to be our approach? x2 will be obtained as x1 plus dx by dt evaluated at x equal to x1 into delta t. Okay. The next step will be that you obtain x2 as x1, that is value at t equal to t1, that becomes the initial value. Find the derivative at x equal to x1, okay, and multiplied by your time step delta t. Okay. Now, graphically when you see here, let us say that the new slope comes out to be like this, right. Then the new value of x, that is at x at t2 will be obtained by this point. Let us say this point, this is your t2 and this is your x2. This is the point which you will get. Similarly, if you keep on going, you will find actually that the solution which you are getting by this technique is deviating from the actual solution, and this solution is going to be very close to the actual solution if you take delta t very, very small. This is a very important requirement. Now, here this method is called explicit method, because the new value of x at any time is obtained in using the previous value of x. That is the, when you are solving this problem, right, we find out the derivative. This derivative is explicitly computed using the known value of x, okay, and that is why it is called explicit integration method. Here in this method there is a problem that in case you take delta t large, right, the error which is created will propagate and the solution may blow off, right, and we call this as numerical instability, right. Therefore, numerical instability is a problem when we use explicit techniques for solving nonlinear differential equations. Therefore, in general you can write an algorithm using this Euler method as x n plus 1 is equal to x n plus dx by dt, x evaluated at x n, that is you evaluate this derivative at x equal to x n, and this is to be multiplied by time step delta t. Therefore, this is the algorithm, a simple algorithm for evaluating or for obtaining the solution of first order differential equation. Now, in case we have instead of scalar equation, we have a set of differential equations, right, then the same procedure is adopted, because these equations are coupled, right, and therefore, when I write the solution, this x will be replaced by vector, that is we will write x, I can write down here, the algorithm will now becomes x n plus 1 equal to x n plus dx by dt evaluated at x equal to x n into delta t. This is the algorithm when you solve a set of differential equations. When I say dx by dt, x is a vector. What is the meaning of this? Now, suppose I say here x is equal to x 1, x 2, let us say I will use the word say x p, I do not want to mix up with this x n, okay. Let us say there are p components, the dx by dt, the meaning will be here dx by dt, this is transpose here, okay. X is a column vector, dx by dt can be written as dx1 by dt, dx2 by dt, dxp by dt whole transpose. It means when I say the derivative of this x means I am taking the derivative of each of the variables dx1 by dt, dx2 by dt, dx. This is the way this is to be obtained, because when you write down the set of differential equations, right, first order differential equations on left hand side we have the derivative terms, delta 1 dot, delta 2 dot, delta omega 1 dot, delta omega 2 dot, like that, okay, for our stability analysis, right. Therefore, these are all derivative terms. These are individually evaluated and put in the. Now, when I say that dx1 by dt is function of all the state variables and initial conditions, right. Now, in order to overcome the problem of numerical instability, this Euler method has been modified to reduce the error which will accumulate and propagate, right. So, that we can use a reasonably large value of delta t, the time step, because if you use very small delta t, then to get the solution the number of steps will become very large and it will take more time for getting the solution, because at each step you have to do the similar type of calculations. In the modified Euler method, the approach goes like this. The first step is exactly the same as we use in the Euler method. That is, we find out the value of x1, we call this is a predicted value x1p, that is the predictor step. The first step is called predictor step, that is x1p is equal to x naught plus dx by dt evaluated at x equal to x naught into delta t. That is, you evaluate x1p, we call this as a predicted value, initial value x naught plus derivative at x equal to x naught into delta t. Okay. Now, using this predicted value x1 is the value at t equal to t1. Is it okay? T1. Therefore, using this predicted value we will find out the derivative of the function at t equal to t1. Okay? And using these two derivatives on predicted value, we will find out the corrected value of x1. Okay? Therefore, the approach, the algorithm will go like this, that x1c is called corrector step, x1c is equal to x naught plus 1 by 2 dx by dt at x equal to x naught, that is what we have already done. Find the derivative at x equal to x naught. Then you find out the derivative of this function, right, dx by dt at x equal to x1p. Okay. And then take the average of these two derivatives, because this is the slope of the solution or to the function at t equal to t naught or x equal to x naught. Okay. This is the slope at x equal to x1 predicted, or we can call it this is the slope at t equal to t1. Okay. We take the average of these two slopes and obtain the value of x1, and this is going to be naturally more accurate as compared to the one which we obtained by considering only this term, because now we are considering the average of the two slopes, right. Now, here one need not stop here, you can use this corrected value, that is x1c, right. Consider this as a predicted value and further you can find out the more accurate value of x1. That is what can be done is that you can call this as x1, I will call this x1 c2, I will just now suppose I use actually one second step, then I will call this as this equal to x naught plus 1 by 2, this initial derivative will remain same, that is dx by dt at x equal to x naught plus we will calculate this dx by dt at x equal to x1c, C1, I will call this as a C1 in that case. If I go for one more step, I will call that this is C1. Use this x equal to x1c, okay, and then multiply by delta. Now, in case actually these two values are very close, you can stop here. Suppose when you find out the corrected value in the first step, then you find out the corrected value in second step also. If suppose these two corrected values come out to be very close, or two consecutive corrected values come out to be very close, you can stop. Now, generally this second step may not be required. You can use a small time step, and so that you can stop at the first correction step itself, right. But if you want to, you can say go for further further you can say a sophisticated value or accurate value, you can use these steps instead of terminating at first corrected value, you can go for second, third, so and so. And since this has to be programmed, therefore it is nothing very big actually so far computations are concerned. You can always develop a program which will do it. Because this type of the modified Euler method is used very commonly, because this is very simple and more accurate also, and we can use a slightly larger time step, and the problem of numerical instability also is less probability. The next step, which is or the next method which is commonly used for solving set of nonlinear differential equations is known as the Runge-Kutta method. Here I will discuss only the fourth order Runge-Kutta method, which is more popularly used, because in the literature the second order Runge-Kutta method, fourth order Runge-Kutta method, these are discussed, right. Now, here as we have seen actually that the Euler method is a first order method, where we are looking in terms of the Taylor series expansion as if we are terminating at first derivative term. Here this fourth order Runge-Kutta method is as if you are using up to the fourth derivative terms. Actually you will not be evaluating the fourth derivative terms, but it mimics the Taylor series expansion as if you have taken the terms up to the fourth derivative. Now, the algorithm for evaluating the value of x at n plus 1th step is x n, that is the value of the variable at previous step x n, plus 1/6 times this term, that is x 1 k 1 plus 2 times k 2 plus 2 times k 3 plus k 4. I will explain these k terms. That is, here what is done is you obtain the value of x n plus 1 in terms of the previous value plus this term. This is basically delta x. Okay. Now, these terms k 1, 2 times k 2, 2 times k 3 and k 4 are defined as follows here. K1 is the f of x n t n into delta t. That is you evaluate this derivative term, that is f of x n t n at t equal to t n. Suppose that we are starting at t equal to t naught, then this will become f of x naught t naught. If it is going next step, it is becoming f of x 1 t 1 and so on. Therefore, this is multiplied by delta t. Okay. Then we calculate k2 as f of x n plus k 1 by 2, x n plus k 1 by 2, and this means actually that the value of this term x n plus k 1 by 2 is at Tn plus delta t by 2. That is, in all the differential equations we come across, right, the time is not explicitly available in the equation. That is, the time is implicit function, right. Suppose if I solve this swing equation, right, in my swing equation on the right hand side, when I evaluated this function, it is function of delta and so on. The time is not explicitly visible, but it is implicit, because delta is corresponding to a certain time, right. Therefore, here when I say that this is the value of x, right, it means it is at the beginning of the interval x n plus this quantity can be considered to be at the mid of the interval. So, that I can say interpret this total term as at the mid of the, and the time corresponding to this will be Tn plus delta t by 2. Okay. This again you multiply this by delta t, so that this becomes a increment in x. K3, we make use of this K2 and obtain this term derivative, that is f of, obtain this function f of x n, same x n remains same, plus K2 by 2 Tn plus delta t by 2. It means again this increment is computed. In the last one, we obtain the function at x n plus K3 full, not half, full, that is Tn plus delta t. Okay. Then what is done is, to obtain the increment delta x, we use these 4 terms, and the weighting given to this K1 is 1, K2 we multiplied by 2, K3 multiplied by 2 and K4 by 1, and then this is added and divided by 6, so that it becomes a weighted average. This is the formula you can see here, x n plus 1 is equal to x n plus 1 by 6, K1 plus 2 times K3 plus 2 times 2 times K2 plus 2 times K3 plus K4 by 6. It is basically, these are all small increments in delta x, and the increment in the small step delta t is obtained by taking the weighted sum and dividing by 6, that is the weighted average you can call it. And here you can easily see here actually that we have not computed the second order derivative or third order derivative or fourth order derivative, but this process gives you the solution similar to what you will get if you include up to the fourth order derivatives in the Taylor series expanse. Now, I shall illustrate the application of these techniques by taking an example after discussing these techniques. When you physically interpret these 4 constants, then K1 can be considered to be slope at the beginning of the time step, that is slope at the beginning of the time step into delta t. Then K2 can be interpreted as first approximation to slope at the mid step, is the first approximation. First approximation to slope at the mid step into delta t. Therefore, we are multiplying slope with delta t, so that this becomes a increment in x. Okay. K3 will be interpreted as second approximation to slope at the mid step into delta t. And finally, K4 the slope at the end of the time step delta t, right. And then increment delta x is equal to 1 by 6 of K1 plus 2 times K2 plus 2 times K3 plus K. This is what is the fourth order Runge-Kutta method, and the simpler form of this is called second order Runge-Kutta method, right, where actually they use less number of terms. Now, we will just discuss something about the numerical stability of explicit integration methods. When we discuss this numerical instability, the meaning is that if the errors propagate and accumulate, then solution will blow up, and although the actual solution is possible to get the correct solution, but by this numerical technique we are getting a solution which is incorrect, and that is what is normally called actually the numerical instability. Now, numerical instability can be avoided by choosing the appropriate value of time step. Now, in any system when you solve, right, the system has a number of time constants. For example, when you consider our stability problem, then you will have the time constants which will be very short, of the order of, we can say, a fraction of second, right, to few seconds. Suppose actually I take the excitation system, right, then if I consider the time constants associated with the sensing and transducer circuit, this voltage sensing and transducer circuit, it is of the order of 0.02 seconds, it is very small. If I take the open circuit time constant of the field circuit, it is of the order of 5 seconds, 10 seconds and so on. Similarly, if you take actually the time constant, the mechanical starting time constant, that is Tm, that is 2h, okay, that is also very large, because h is of the order of 5, 6, so that Tm becomes around 10, and therefore, we define what is called a term a stiffness of the system, which relates the ratio of largest time constant to the smallest time constant. Suppose largest time constant is 10 seconds and smallest time constant is say 0.02 seconds, then this ratio determines represents the stiffness of the system, right. The stiffness is defined in terms of another term which is called actually the largest value of the largest eigenvalue of the linear system to the smallest eigenvalue. That is, you take a system, find out the eigenvalue and find out the magnitudes, largest eigenvalue divided by the smallest eigenvalue. This will give you the measure of stiffness of the system, and for the system to be for the solution to be numerically stable, right, the time steps should be related to the smallest time constant, right. And here we discuss one more important technique where the numerical stability is not a problem, okay, and that technique is known as the implicit integration method. We will first understand conceptually what we mean by implicit integration method. It is a very simple approach. Again, we start with the differential equation dx by dt equal to f of x t, x equal to x naught and t equal to. Let us say that this is a scalar equation. To start with, let us consider a scalar equation. Now, I want to solve this equation. How do I solve this equation? Let us say I want to solve this equation. The one simplest approach would be you integrate both sides. Suppose I want to get the solution of this equation, dx by dt, which is a function of x t. You integrate this equation with respect to time, and I want to integrate this over a time step, say t naught to t1, dx by dt क्या, this can be written as integral of f of x t dt t over to t 1. Now, what is the, suppose you integrate and obtain actually this value, what is the value of this? Huh? Delta x, or if I call this as x1 minus x naught, that is I am integrating dx by dt with respect to t, so that it becomes the integration of dx only. So, that we can say that at t equal to t naught its value is x naught, t equal to t1 its value is x1. What is the integral of this function? What is the value of this integral? Therefore, we can say that this is the area under this curve from t naught to t1. Okay. Now I can, because this area I cannot find out, because I do not know how this function is varying, and it is a non-linear function. I do not know. Therefore, what we can do is that, suppose I take this situation. If I plot the function f of x t as a function of time, as I plot this function f of x t as a function of time, and let us assume that this is the actual solution. Okay. Now, as you very clearly told actually, that if I am trying to evaluate this integral, then it is the area under this curve from t naught to t1. Okay. Now, this area under this curve can be approximated by the area of this trapezoid. Only error which will cause is a small error, that is, you can approximate the area under this curve from t naught to t1, the small time step delta t, as f of x naught t naught plus f of x1 t1 multiplied by delta t by 2. Is it not? This is very important step actually. People sometimes actually fail to appreciate this step, but it is very simple step. This is the most important step. Again, you can see here actually that actual area under this curve and the area which is approximated using the area obtained by trapezoid, right? There is a slight difference, and this difference can be reduced if I take delta t as small as possible. You reduce this delta t, this difference will also vanish. Okay. Therefore, I can say now that x1 can be written as, from that equation, as, because we are at x1 minus x naught, let us put x naught on this side, x1 can be written as x naught plus delta t by 2 f of x naught t naught plus f of x1 t1. Therefore, this is the value of x1 obtained at time t equal to t1, but the problem here is that this x1 is expressed in terms of x1 itself. Here, if you see this step, in this step what has happened is that x1 I have expressed in terms of x1 itself, but this equation is now an algebraic equation. This is a non-linear algebraic equation. Okay? And therefore, this non-linear algebraic equation can be solved to obtain the value of x1 using standard standard techniques like Gauss-Seidel, Newton-Raphson techniques, which are used for solving the non-linear algebraic equations, because this is the algorithm can be written as x n will be equal x n plus 1, let us say x n plus 1 will be equal to x n plus delta t by 2 f of x n t n plus f of x n plus 1 t of n plus 1. This is the algorithm, but I think you appreciate that you have to solve this algebraic equation, nonlinear algebraic equation, using again numerical. This is what actually I have just written here. Now, to illustrate actually this trapezoidal rule of integration, let me take the tangent stability problem of a machine connected to infinite bus. We will take a classical problem. The differential equations which we have to solve can be written as d delta omega equal to 1 over 2 h p m minus p max second differential equation is d delta by dt equal to delta omega into omega naught. These are the two first order ordinary nonlinear differential equations. Now, these two equations are coupled equations, that is, you will find actually that in this equation delta term comes, right, while in this equation omega term comes, delta omega terms. Therefore, in general you will find that if you take any problem for a stability analysis, you will get a set of ordinary differential equations, ordinary nonlinear differential equations, but they are all coupled nonlinear differential equations. Okay. Now, let us see that how we apply the trapezoidal rule of integration and what equations we will get. Okay. Let us assume actually we know that at t equal to t n, at t equal to t n, delta equal to delta n and delta omega equal to delta omega. Okay. That is, at time t equal to t n, we know the value of delta as delta n and omega as omega n. Okay. We write down now the two first order two nonlinear algebraic equations by applying the trapezoidal rule of integration. That is, I consider the first equation. I am to obtain this term delta omega n plus 1. This will be equal to delta omega n plus delta t by 2 here I have to write down here f of x n t n, f of x n t n. Now, in this expression I will write down here 1 by 2 h, I am not substituting the values, 1 by 2 h P m minus P max sin delta n, correct. You can close this bracket here, plus 1 by 2 h, P m remains same, P max sin delta n plus 1, you close the bracket here, and this is the equation to obtain the value of delta omega n plus 1 in terms of delta omega n and in terms of delta n plus 1, because now delta n plus 1 is coming here. The second equation we write down here will be delta n plus 1 equal to delta n plus delta t by 2 multiplied by f of x n t n. Okay. Now, in this case it is delta omega n into omega naught plus delta omega n plus 1 into omega. Okay. Now, these are the two nonlinear coupled algebraic equations, okay. And initial values of these quantities are known, delta omega n and delta n initial values are known, okay. And you use the simplest technique like Gauss-Seidel technique to obtain the value of delta omega n plus 1 and delta n plus 1 at t equal to n plus 1. Numerical stability of these techniques can be illustrated considering a set of linear differential equations. Let us examine the equations written by this in the matrix form x dot equal to a x. The value of x is known, say x n is known at time t equal to t n. We want to obtain the x n plus 1 at time t n plus 1. This represents the set of linear differential equations, and applying the Euler's method we can write down x n plus 1 equal to a x evaluated at t equal to t n plus x n. Now, we can write down this equation in the form x n plus 1 equal to I plus a delta t into x n, which can be written as f function f into x n. Now, this represents discrete form of this differential equation x dot equal to A x. Now, for the system to be stable, the eigenvalues of this matrix A, matrix F, not A, matrix F, which is equal to A I plus A delta t, must be must lie in a unit circle. That is, the eigenvalues, all the eigenvalues, that is lambda j for j from 1 to n must lie in a unit circle, that is magnitude lambda j must be less than 1. Now, here we can see that the matrix F is function of the time step delta t. As the time step delta t increases, the eigenvalues of this matrix F may lie outside the unit circle, and the system response becomes unstable. Now, here a small correction. When we write down x n plus 1 equal to A x t equal to T n, this should be multiplied with delta t. Now, with this I conclude my today's presentation by saying that we have discussed the various numerical techniques which are suitable for solving a set of ordinary nonlinear differential equations. Thank you.